confused. I'm Boris, he is Stavros. I'm taller, I have more hair, he is better looking. So what are we going to talk about? We're going to talk about machine learning, but really very, very little. We will talk about models, we will talk about what we're trying to build, and we will discuss the results that we have achieved and what we're going to do next. Just for your information, this is the first of the presentations on this topic. There is an excellent ING presentation tomorrow about very similar topic. Buzz paid me to announce this. And there is also a very similar presentation from Radical Beat. We are working together with these two companies, so we are kind of aware of what they're doing.
Okay, so when people think about machine learning and they try it out, they just think that it's just magic that works out of the box, and you apply it to your data, and then everybody is happy. Your business guy is happy, your data scientist is happy, and happiness is all over the place. But reality kicks in, and so when you need to apply machine learning, you need to follow a life cycle. You need to sit down with your business guy, describe the strategy of your business use case, see what are your data, what are the goals there, how you can set experiments, set up your hypothesis for your experiments, and then you need to define your models, and before that you even need to prepare your data to apply the models on them, and then you need to tune your models and move on with applying the models in production, deploying them in production, and then get results so you can go back and do the same thing. Now, in this talk, we focus on the last part, which is putting models in production, because this is highly related with FlinkML's roadmap. So to provide you with some background, more or less you know that FlinkML is about the API that is established for a long time. And lately, the community decided to put some effort to surface what are the other opportunities for Flink and machine learning. There is a document about FlinkML which describes the roadmap, and it's mostly about some efforts that are now happening about FlinkML and next steps. One of these efforts is this, Flink and model serving through Flink. It makes total sense because FlinkML has excellent guarantees about throughput and latency. These are things you need for model serving. And model serving is, for many use cases, something that it needs real-time support. You need to make predictions, for example, in several milliseconds. And that was the reason we also participated in this effort. But also there are other guys, and as Boris said, there's also ING, Radical Beat guys, Aaron Wright from Dell EMC. We are working closely on this to move things to the next level. So, as Boris said, we're going to talk about models. Models, what are models? Models are an abstraction of reality. For this context, it's just functions that have inputs and outputs. Here's an example of linear regression, a trivial model. And the good thing when you describe things as functions is that you can create compositions of functions, which also reflect how, at the end, how you deploy stuff in production. Now, besides the common notion of models, there is this also abstraction of model learning pipelines introduced a few years ago. It's common, found in many frameworks like scikit-learn, SparkML, TensorFlow. The idea here is to put things together because inputs and outputs are tightly bound to the model. Now, when we say model, it can be a single model, like a regression model, or a combination of models, like when you have an ensemble or segmentation or composition of models. So this creates requirements for your model when you put it in production, requirements for memory, for processing, and you have to have all this into your mind when you deploy stuff. But this abstraction is a good thing because it puts things together to allow optimization and better testing. It's similar to what you have when you have pipelines in software engineering, when you deploy software and you go through several stages until things are in production. Now, models are everywhere. I mean, data scientists create their own models. There are models in production, how they correlate. I mean, a data scientist will do his work with whatever tool he has available. He doesn't care how things should be applied in production or how things are going to be controlled, or how a data engineer do his work to put data scientists' work in production. So there is a gap. Obviously, this happens a lot in the industry. It's pretty common. How you can fill this gap? The way to do that is through one way to do this is through standardization. So Boris is going to talk a bit about standardization.
So what is happening there is people started talking about exporting model. And this becomes very important because of two reasons. On one hand, when you export the model, you have the common representation regardless of the framework that was used to produce this model. Another thing that is important is that what you are importing is effectively not the code, but rather the descriptor of what the model does. And this is very important for our overall solution because it allows us now to treat the model as a data, which means that we can treat both model and the actual incoming data in the same way. And there are several ways of exporting the model. There is PMML, predictive markup language, and guys from Radical Beat are going to talk significantly more about it. There is another option, which is a newer standard, which is PFA, portable format for analytics. And then there is yet another one, which is not really a standard, but it is used so widely that it becomes de facto standard. And if I'm correct, Aaron White, 6 months ago in California at Flink Forward was talking about usage of TensorFlow with Flink.
Okay, so since this talk is about model serving and building a system for serving models, there are some considerations about models and their life cycle. So models usually change, right? So you deploy once a model, then you find that you need to tune it, and then you redeploy it. So this also means that you have to keep track of model versions. You need to also follow some processes for deploying your models, and this also is highly connected with what your company does. What are the processes they have, and how this relates to model deployment. Also, there are requirements for the deployment itself. So you need to quickly respond to predictions. So when you have a query for a prediction, you need to get the result back fast enough for the specific use case. Also, it may be the case that you have many deployments, and this is also happens frequently. You have many models, or one model that is hit many times, and you need to have a high throughput. Now, it's also important to support model update in a way that is fast enough for the rest of the software pipeline. And at the end, you need also to have reliability. If something happens and things go wrong, you need to be able to restart your deployment. So another thing besides that is model governance. A model, as Boris said, is data at the end of the day. So they have to follow some rules. They need to be governed by a company and have some follow some guidelines about who is using them and who is actually responsible for the deployment, and how it is possible for all the people who are related to the model deployment can look at them and search about their deployment characteristics and performance and all that stuff. It can be data scientists, it can be someone who's at the business level, and something more. I mean, there isn't just about it isn't just about who is responsible for the models. It's also about security. Lately, there is some work about model security. It is possible to actually reverse engineer the models and through public APIs and see what the models is about, and actually it could lead to sensitive data leakage. So it is also important to consider your model as part of your data governance strategy. There are many more. I could talk about model security and privacy, but there's no time. Anyway.
So after this prolonged introduction, let's actually talk about what we're trying to build. So this is a reasonable overall architecture of the implementation. So as I said before, we are treating models as data. So we have two sources of data, data source and model source. They are all streamed to the stream engine. The stream engine contains the current model because the model itself can be quite bulky. The model could be streamed in the engine either by value or by reference. It can be located in Cassandra or on HDFS or on S3, and we are just pushing the reference to it. So in order to do this, we first have to export the model, and the popular exporter tools. There is a great tool for PMML, which can work with SparkML. And for TensorFlow, we were trying two types of exporting, the normal graph export and the newer safe model format. So it turns out that Flink is an ideal platform to implement the architecture that we are talking about. So Flink low-level join is doing exactly what we need to do. So it takes source one, which is the model source, and it creates the state inside the Flink so that for the model you don't have to go anywhere outside of your stream processing. And the second source is the actual data, and it gets the model from the current state, and it basically does all the calculation, and the result can be used for the subsequent stream processing operations. One of the questions, I was talking about this with Till yesterday, what do you do if you don't have the model in place yet? We took a shortcut. If there is no model, we're just dropping the data on the floor saying there is nothing to do. But in general, the conversation is that in general, you can use open method on the Flink join to populate the model from a well-known source, but apparently input streams, side inputs are going to provide a little bit cleaner semantic for this. So in order for us to be able to do this, I'm sorry I'm rushing a little bit. I have 4 minutes left, and I have 5 more slides. So what we're doing is, on the wire, we're using protobufs to represent both model and the data. And it works out quite nicely because the content of the model itself is just a binary blob. And the metadata around it is what actually is represented by the protocol buffers. And this makes it very simple to do transparently passing by value or passing by reference. Inside the implementation, we are using a very simple trait, which is a model trait, which can have its implementation, for example, using PMML evaluator. It can have its implementation using TensorFlow Java APIs. Now, when we are talking about joins, Flink allows us to do two types. Wow, I'm doing great on time. I can slow down a little bit. Flink allows us to do two types of joins. There is a key join, which you guys, for those who were at the training yesterday, they had a great session describing this in the glory details. But the idea here is the model and the data have the keys. And if they have the same keys, then this model is used to score this data. And if you do this, then Flink does the distribution. So it works really well if you have a lot of models that you want to score in parallel, and the key distribution is more or less even. If your keys distribution is not very even, Flink provides partition-based joint. So in this case, let me go back for a second. So what is happening in this case, why it has its own SLA, is because the model with the given key will be always scored by the same executor. So obviously, if your keys distribution is very uneven, one of the executors is going to become very hot. So to avoid this, you can use the map joint. So the way map joint works is slightly different. If you think about Kafka as being your input stream, then what is happening is partitioning your data in Kafka will define which executor is going to execute the certain things. What is happening in this case with the model stream is broadcast to all the executors. The caveat of this is because broadcast time to different executors is unpredictable. You can have jitter, so you can have data served by the new model, and then the next executor will serve it using the old model, and then it will go to the new model again. But if you're okay with this little jitter, this actually scales really well. If you have more than one model as a state, you can just use the map which Flink provides, and you can serve as many models as you want. The next big thing is monitoring. If you are doing model serving, you would like to know what exactly going on, and you would like at least have something like this. The traditional ways of doing this is through logging, which is not very nice. I was glad to see that Flink now did integration with InfluxDB, which automatically integrates with Grafana. So you can put some of this data in Grafana, but Flink itself provides the beta mechanism for this, which is a queryable state, which we experimented with, and it works quite nicely. It has one drawback. In the current implementation, the queryable state works only for the keyed partition, for the keyed joint. It doesn't work for the partition joint, but again, I was talking with Flink guys yesterday, and they were promised that in the next 20 years, it will work just fine. So where are we right now? So the proposed solution basically doesn't require any changes to the current Flink implementation. It can be just a nice model serving framework on top of Flink. we are in the process of completing Flink improvement proposal. The code is available in the Flink GitHub. We already put the first version there, and we were looking for more people to start participating in this effort. And what we want to do is we want to complete the proposal document as quickly as we can. We want to bring additional model implementations, work with Aaron from Dell on the TensorFlow, work with Radical Bit on PMML. Look at the model governance, which is going to become more and more important. And I made it nearly in time. So you still have an option of asking the question. No, look, hey, you have to ask questions first. No questions? Then you can clap again.